Okay, I think we should get started here. Um, Let me first of all pause here. Okay. Okay. I think for we missed Monday's class, and that's why we did not have the lab on Tuesday and Monday, so that we are in sync with each other. So we'll try to cover that next week, Monday and Tuesday. So my plan is I will try to see how far that will be, how that would occur. What I mean by that is usually we have the lab, the data treatment, and by that time I should have introduced you to the next set of experiments. So I'll try to do both of those things. If not possible, I'll just cover the data treatment, and then we have 1 week towards the end of the semester. I might stagger that. That's it. Okay. So that is my plan. So let's get started here then on chapter number 5. I had asked you to read this, but when I've thought about it, when I've thought about this, I think it is a good thing that I go over this such that every one of you, we are on the same page. Okay. Now, the first thing here is to talk about signal and noise. And so when we talk about signal and noise, we have to know what noise is. A noise, whenever you get any unwanted signal in your measurements. So let's put this in perspective. For people who are in radio engineering or engineering in terms of receiving signals, that's a familiar term. And there are books on this that have been written on engineering signals and so forth. So this is a term that is just borrowed. It is borrowed from radio engineering, noise. We want to define what noise is. Noise is a term borrowed from radio engineering. It means, for example, if you tune up your radio, as you drive around and tune up your radio, sometimes it picks up some other noise, right? So that extraneous noise from different frequencies, that's not what we need to hear, okay? So that particular interfering frequency is what we call noise, other than the target frequency. So in terms of physics and chemistry, so noise is any extraneous or unwanted frequency. So you're going to see here, it is unwanted. And it's extraneous, any extraneous from outside. And what does that mean? Sometimes, for example, when I drive around listening to the radio, sometimes it can it can obscure your frequency, right? That is possible. So sometimes it can be superimposed on the signal. It can lower that signal that you receive. In the same manner, when you are in the lab, for example, you are acquiring some spectrum, for example. Unless that signal is so large, unless your analyte signal is larger than the noise, if they are of the same level, you might not distinguish between the two. So we are saying here these extraneous and wanted signals can be superimposed on the analyte signal in the lab. And so this is an important thing that we need to be aware of all the time. Okay? So the other thing that we need to be aware of is the fact that every measurement has two components. One of them is the wanted signal, the spectrum, that's the peak that you need in a spectrum, right? You'll see that all the time. Often in the lab, in chemistry, we get this spectra that we want all the time, all right? Or even if you are doing some biology and you're seeing a signal on the cell, there are particular signals that you need, okay? If it's proteins, a protein signal that you need, but sometimes you get others. So there is the wanted signal and the unwanted noise. Now we can comfortably use that term. the unwanted noise, anything else that you do not want. So you have to distinguish the two. So sometimes this noise is very apparent. You can see it. This is the noise. It's not what I need. And other times it is so small that you can ignore it. Those are the two scenarios. It's very small. And that's why we define sometimes the two terms we defined earlier in the introductory chapter. What are the two terms? We talked about LOD and LOY. Q, LOD, the smallest that you can detect with confidence, all right? So sometimes you can ignore it. If it is in the LOQ, if the LOQ is 10 times more than what it will be, then it means you can ignore it. And so in this chapter, this is what we discuss, therefore, some of the common sources of noise and how the effects of the noise can be minimized. Now, we all know all instrument measurements involve a signal. You're going to measure a signal. That's how we make judgments. So you're going to have a signal. And unfortunately, the signal always has noise. And sometimes the noise is so large, sometimes it's so small, you can't see it, you can ignore it. Let's go to the math here on how we define a signal. Now, we want to be sure about this. Look at the first point, that the signal to noise ratio is one of the parameters that we use. Okay, signal to noise ratio, SN, is independent of intensity. Signal to noise ratio is independent of intensity, and the absolute signal to noise ratio level is usually constant. And a big signal, for example, maybe on Friday, I'll give you some examples during the recitation. We'll work through some examples on this. The big signal has a lower signal to noise ratio. You can distinguish because signal to noise ratio. Does that make sense? You have a noise, you can see it, but the signal is so large. The signal to noise ratio, therefore, is a large number. So you sometimes have to work with that. So the signal to noise ratio, as you see, is a better parameter than just knowing the noise level. Okay, by definition, the signal to noise ratio is defined as the mean X bar. So this is the physics representation of the mean, X bar, and I'm going to do this in the next slide, X bar over S. S is just the standard deviation. Signal to noise ratio is equal to the mean over the standard deviation. And you know how you get the standard deviations, class. You know how to get the standard deviations. You have to get some, if you do this, and you have these signals here, okay, and you're going to get the standard deviations of peak-to-peak measurements. Are we together there? Peak-to-peak measurements from the background. This is the background here. So you measure one peak and another peak and another peak. You get the deviations, right? Remember, the deviation squared over the number of those peaks. Does that make sense? Then the square root of that, the sum of the deviation squared over n minus 1, if it's a smaller sample, is the square root of that. That gives you the standard deviation. So you know how to do that. The mean you can measure very well. So it's equal to the mean over the standard deviation, and signal to noise ratio has these two. This is one formula, the mean over the standard deviation. The other one is the signal to noise ratio is equal to 1 over RSD. In other words, this signal to noise ratio is equal to signal to noise ratio. We have already defined it as the mean. So the mean over the standard deviation is equal to 1 over RSD, relative standard deviation. Let me go to the next slide to make this clear. So this is the signal to noise ratio here, which we are talking about. Signal to noise ratio, a better parameter. Let me repeat this again in this next slide here. So we have already said this. So the signal to noise ratio is a better parameter, as I've said, and it shows you the quality. It describes the quality of the data. Okay. So the signal noise ratio is a parameter describing the quality of the data that you get. And so that is important as it's the quality. This, if you talk about something that describes the quality of the data, we use what we call the figure of merit. Are we together there? One of the figures of merit. So if you have the data, and you know now you go into the regime of statistics in order to help you know how your data is. You get the average, you get the median, you get the mode, all those descriptions, right? So, but signal noise ratio is another one. And I'm not going ahead of myself, but, and you see when you buy an instrument, normally this what instrument vendors are going to tell you, oh, we have a good instrument. You want to buy it? The signal noise ratio is 800. Does that make sense? That's a good number. If the signal noise ratio is 800, what does that mean to you?
Signal 8 times bigger than average noise.
Which means
That the signal is very distinct.
you are in a vendor with vendors, and they give you that number. They give you, let's give two numbers, 800, and another machine, 1,000. Which one would you go for? 1,000. Because you can distinguish it, right? And usually that's what whenever you buy any instrument, they will have to tell you this number. Does that make sense? How good it is. And that means the resolution is good as well. That means the detectors are very good to distinguish noise from the signal. Okay, so that's a better parameter. And so it's a marker that is used in describing the quality of an analytical method as well, or the performance of an instrument, as I've said. You see, I've already mentioned this. We use these figures of merit, and some of the figures of merit, as I've mentioned, will be the mean, the average deviation, standard deviation, LOD, LOQ. What else did we talk about the figures of merit, if you remember? Basically, those are some of the ones that we've talked about. Those are figures of merit. Are we together there? And this is one of them, the signal noise ratio. Okay, and so we have already gone through this signal noise ratio. It's the mean of the signal, you go to the previous slide, over the standard deviation, and the mean of signal x bar over s, that's the standard deviation, equals 1 over RST. So note this formula very carefully, because sometimes in an equation or a question, you might be given one of them and be asked to calculate either the signal noise ratio or the average or whatever the question asks you. Are we together there? So just note that you can relate the two formulas. Signal noise ratio, the mean of the signal over the standard deviation. And you see, if you do this, remember I tried to show you a picture of how you can calculate typically the signal to noise ratio from spectra. Did you realize what I was trying to do? I drew a picture, right? And told you this is what you get from the instrument. So that's the typical question. It's just not only the numbers. You can be given a graphical representation. Does that make sense? Graphical representation, and then you'll see peak to peak, peak to peak, and you have the average. Sometimes I have a question, I think I would bring it forward. So for example, what I've said here is you might have, this is the average, and all of a sudden you get a peak. Does that make sense there? All right. So typically you would have to measure this distance here. And I have a question of this nature. You measure that distance here, okay? From just the average, and then from there, this peak is simply the signal. That's how far the signal is. Remember, it's the mean of the signal over the standard deviation. And sometimes you might have to do peak to peak, peak to peak, peak to peak, average them. So you get the average, you get the standard deviations. Then you might get the signal to noise ratio. Remember, this, why I'm putting my fingers here, what is this distance here from the here? What is that distance?
It's the noise.
This is the noise. Does that make sense? Is everybody clear here on what I'm trying to illustrate? This is the noise level. Does that make sense? That's the noise level, and that's about the signal. Make sense? So the noise level, this distance here from the noise level gives you the signal. Does that make sense? The signal, or the signal height, or distance, whatever you can call it. And then you can measure that relative to just the standard deviation. I'll bring this question to you, and sometimes I give it, and some people don't make sense of it. Okay? So it's applying the formula. So relative standard deviation, we know, and where S is the standard deviation of the measured strength, as we see, and we know all that X bar and so forth. Let's be clear now. Here is what was done in the lab. This was done in the lab. You see, and this is represented in your textbook. Consider A and B, and this is an NMR signal, an NMR spectra of progesterone. And so you can measure this using the NMR. We used to have an NMR here, 400, we don't have it. And we have the smaller ones, the 100, 120, 80 mega in the lab, okay? We're together there. So you can measure using progesterone, gives you a peak. Now, notice here, this is what it gives you. And if you know the structure of progesterone, right? I don't know it offhand. Are we together here? So, but you're going to see it has particular peaks here. So let me remove this standing between us to see at the bottom. You see, this is the frequency in hertz. Does that make sense? So if it's, for example, 0 to 400 megahertz, it may be a carbon-13 peak where you are going to observe some signals, all right? If it has an amine, if it has a carboxyl group, we're together here, or a carbon-oxygen bond. So that's what you're going to see in your done organic one. How many have done organic one? Okay, I'm talking familiar people here. You know how to piece the structure together, right? From carbon-13, infrared, spec, you know that, right? So now we're on the same page now, okay? So this is one of those peaks. And then you can say, well, it has these functional groups. Now let's now get to the heart of this, of what this is telling us. So the first one, see, the first one is a measurement. So A, you can see A, notice here. You can see the peaks there. Can you see them? Are you confident of those peaks? A, the trace A. Look at it. Unless you have a trained eye, it's not even with a trained eye. Sometimes you're going to guess and say, well, maybe I have a peak here. Maybe I have a peak here, right? Because it seems to come above the background. Does that make sense there? Maybe, but I'm not so confident because there are other peaks as well. Does that make sense? Then maybe here is another peak as you interpret spectrum. Maybe here is another peak. Maybe here is another one, then another one, maybe another one. But these ones, I don't know. Until you, again, how do you increase the signal? How do you increase, how would you be confident that these particular signals that are at the baseline, how are they real signals? What you will do is you would acquire this spectrum for a longer period of time. Does that make sense? You acquire more scans, we say. You acquire it for a longer period of time. That means you are accumulating those peaks. We together, they are real signals and they are not noise. Remember we say noise is what?
Wanted.
It's unwanted, but it is. Go back to the first sentence. Go back. On that slide. Constant. You see that? Noise is always what?
Constant.
Doesn't change. So, but when you increase more scans, if there is a peak, you accumulate those signals and they increase. Does that make sense? The noise is constant, doesn't change. Okay? But you accumulate the signal, then you would see it increases. And that's the case for this one here. Part B is, notice, there is very little confidence in the ability to determine the peaks at a lower signal noise ratio. Maybe the one in the middle here, I might say, well, maybe those ones. Does that make sense? Maybe those ones might be peaks, but I'm still not confident. Then you go back and accumulate more. Instead of taking 10 minutes, you go 20 minutes, you go 200 minutes, and those peaks, the analyte peaks, would accumulate. Are we together there? That therefore means now, look, there is a signal, right? It's the analyte peak. Look at the other ones. I was doubting these. They are there. Can you see them, class? You can see. That's why I said a trained eye, you can pick some of these if you do this again and again. So here are peaks. Then you see another peak. And then this shoulder peak here, you can see. Then you can see. That's what I'm saying here. These seem to be peaks that correspond to what you see up here. This one, obviously, you can see. And then you can see a shoulder peak here, which is now evident. You can see it here. Then you can see another one now. But here, this was just noise. Does that make sense? That was noise, although it seemed to be peaks. And then this is simply, notice here again, this is another peak. See this one here? Does that make sense? Looks like. So now, how was this second spectrum acquired? It was acquired simply by just spending more time, and you increase the signal noise ratio. This is why we pay people in the lab to acquire spectra for us. We pay them, or if it's a lab that does this all the time, you pay them what did we say? You must have a skill in order to do what with an instrument. When you work with an instrument, does that make sense? You must have a skill, and instrumentation is very expensive. Okay, so I'm just saying this. These are peaks. Notice this NMR spectra. For the first one, the signal noise ratio is 4.3. Now this for B, where we see these peaks that we have just distinguished, you can see here the signal noise ratio is about 43. So the detection limit occurs usually at a signal noise ratio of about approximately 2 or 3. Detection limit occurs at that. Remember how we define detection limit? Remember the formula of a detection limit? LOD equals 3 times standard deviation, all right, over the slope. Okay, that's what we defined it. So that's why this is important. 3 is often taken as 99.9. 2 standard deviations, that is a confidence level of about 69%. Okay, so that's what we are saying here. Now let's continue here. Notice here is another diagram. I picked this diagram just for illustration. You have listened to the video that I've put out online as well. You can see at the very bottom, those ones in gray, these are just the noise. They are at the background. They hover around the zero. Does that make sense? They average zero usually, up and down. So whenever you acquire a spectrum, and if I'm in the lab and I'm seeing a very small spectrum, or it's a chromatogram, I tell the students or even myself, zoom in. I want to see what's there. Sometimes when you zoom in, you see much more than what you can see. But when you show me a spectrum and I ask you, can you zoom in? There's something I'm trying to get. Are we together there? It's not that I'm testing you, I just want to see, is that true? Are you sure that what you're showing me is not hiding any information? So this diagram here, what you see is all those peaks up and down around zero. Then those ones in red here, this is the chromatogram, the signal intensity on the y-axis, then on the x-axis, you can see how it was acquired. So X, that is whatever it is. And then notice what you have there. And it is actually, it's normalized, almost normalized to 100%. So on the y-axis. So you can see all those in red, those are real peaks. Sometimes you might not be confident on this third peak because it seems to be showing a signal that is also close to other signals, like this signal here. You can see. So that is important. Okay. Now we have defined noise. I've dwelled so much on noise, on this parameter signal noise ratio. What are the sources of noise? I'll go through this very, very quickly. There are two types of noise that we encounter in chemical analysis. One is chemical noise, and the other one is instrumental noise. Those are two types of noises that we get. For chemical noise, usually is influenced by such things as temperature, pressure, humidity, etc., and by fluctuations in your measurements. And these are usually, the chemical noise usually comes as a result of having uncontrollable variables that influence the system of whatever you're analyzing, of the chemical system that you're analyzing. But instrumental noise is noise from instrument components. Instruments have, the noise comes from the components. And so we have these various types of instrumental noise. Thermal noise, also known as Johnson noise, after the person who just worked on this for a long time. Short noise and flicker noise. Remember last time on Friday I told you, okay, you know flicker noise, right? I want to deal with each of these, the instrumental noise, thermal noise, short noise, and flicker noise, also known as 1 over F, 1 over the frequency noise. Let's go to these categories, which we have said, of instrumental noise. Remember, we have those, I've already defined them here. Notice here, thermal noise, short noise, and the flicker noise. And let's go to each of them. And here, my emphasis here in this, I would usually give you these formulas in an exam or in the quizzes, but you have to know how to use those formulas. I'm just putting there ahead of what I'm saying. Are we together here? So each of these, there are formulas to define each of them. So let's now talk about these categories of instrumental noise. Thermal noise, also known as Johnson noise or Nyquist noise. And some of you may be curious. You can go online, you can see in books, you can read about this. You physics majors deal with this a lot. So the other one is short noise, short, right? You know, some of these terms, when I think about them, they just make sense to me. You talk of a short circuit, right? Why do we call it a short circuit?
Because the energy burns the material of the cables.
Why
It disrupts the flow of current.
shock? It's a current. It occurs very fast, right? So we say, don't put your hands to the circuit or else you become a conductor, right? What are you trying to do? What did you say, sir?
Complete a circuit.
You complete it very quickly, right? Very quickly. So I was walking at night over in the second floor, where the second or third, and I saw they put a relay on the bottom, the circuits there where you plug in. I said, wow, this is very nice, I think. But we have adults here, right? We don't have children here. You know what I'm talking about? Because what will they do? They just poke it, right? They become short circuits. So let me talk about that short noise. Next is flicker noise, 1/f noise, and then environmental noise. These are categories of instrumental noise. So let's go to each one of them. Thermal noise, it is thermal. It is connected with temperature. So here, Johnson noise, as we call it, is also white noise. And I want you to notice this. These are things I test you over. Which noise is independent of frequency? Are we together there? One of them is what? Johnson noise. It's independent of frequency itself, and because it is thermal noise, also known as Johnson noise, it is the thermal motion of electrons. If electrons are moving, when can you eliminate thermal noise?
When it's not moving.
Yes, when are they?
Like absolute.
Yes, at 0 K, right? 0 K, everything comes to not moving at absolute temperature. So that's why, for example, you measure things with liquid nitrogen, you try to bring it low, or if it's NMR, we try to bring the temperatures low. So thermal noise of electrons, it will occur even in the absence of current or a resistor element. Does that make sense? Because of the very precise fact that everything is at motion until you are at 0 watt. Okay. So thermal noise is there all the time. Remember, we are dealing with instruments and the noise within instrument components. So as long as you're above 0 K, Johnson noise is always present because the electrons are moving, right? And now, this is a formula I want you to now to note. The root mean square noise voltage. This is the Johnson noise. Is that new bar? New bar, this one, random, otherwise it is, I take my pen. Okay. All right, this is random mean square, that's noise. And what is the units of this? It's already there. It's voltage. So when you work through this, its voltage is equal to, I want you to notice the formula. It has a component of temperature because it's thermal noise, right? It's equal to the square root of 4K. K is a constant, is a Boltzmann distribution constant. T is the absolute temperature, and we are working with conductors. Every substance has some resistance, so it's R. See R. R is the resistance of the resistive element measured in ohms resistance. And then you have, this is K, the Boltzmann distribution constant, 1.38 times 10 to the minus 23 joule per Kelvin. Okay, and then you have here, T is the absolute temperature. If you are given temperature in degrees Celsius, you better convert it into Kelvin by adding what? 273, if you want to be accurate, 273.15. This is a typical question I give you. I give you the formula to see if you know how to use it. So for KT, again, this is the same square root. You put everything to a half. This is square root. It's the formula. So this is what we are saying here. Now, there is something I have not mentioned here. This component, delta F, that is the change in frequency. I want you to notice what we are saying. Johnson noise is independent of what? Frequency. But it is within a particular bandwidth. We call it a bandwidth. So make sure you know that. It's independent of frequency itself. It's independent of frequency itself. And Johnson noise, sometimes we call it white noise. Why is it called white noise? Why white light? Because it has various wavelengths, right? So it can occur in various wavelengths, but it's within a bandwidth. We are concerned with the bandwidth of all this spectrum. That's why we say it is independent of frequency itself. Does that make sense? We are concerned with the bandwidth. It's occurring within a certain bandwidth. So we have defined this, and so that is again the formula, and you have thermal noise can be decreased. Look at the formula. How can you decrease thermal noise? The answer is in the formula. How can you decrease it?
Lower the temperature.
That's one, until the motion is low. What else can we do?
A smaller bandwidth.
So if you have a smaller bandwidth, that will also be, all right? You can't change the frequency. It occurs within all the frequencies. What else can you do? Look at the formula.
Lower the resistance.
Lower the resistance by using a material that is less resistive, right? What we use for our wiring are copper wires. What we use in instruments will be wires, right? So you use a material that is resistant, less resistant, right? Like copper wires. So that is, it can be decreased by, everybody has written that. I don't need to go through them, right? So by lowering the electrical resistance of the instrument circuits. Number two, lowering the temperature of the instrument components. What else can we do? We have also narrowed the bandwidth associated with delta F. Okay, and we have emphasized this. Although thermal noise is dependent on the frequency bandwidth, it is independent of the frequency itself. I think that is clear. Now we've talked about white noise. By definition, remember, Johnson noise can also be loosely be termed as white noise, but it's not strictly white noise, right? Are we together? We have to understand why we are calling it what? White noise, because it occurs at all frequencies, just like the electromagnetic spectrum. By definition, it's important to note the thermal noise, although dependent, we have talked about that, is dependent on the frequency bandwidth. It is independent of the frequency itself. For this reason, it's sometimes called white noise by analogy to white light, which contains all visible frequencies. And we have also said this, made a note of this, also note the thermal noise in resistive circuit element is independent of the physical size of the resistor. It's independent on the physical size of the resistor. Okay, now I'm going to go here and bring an interesting question that makes use of this formula on Johnson noise. Let's call this rise time and delta F. What we mean by rise time. So delta F, what's another word for delta F again?
Bandwidth.
Yes, the bandwidth within that bandwidth, the frequency. So that's the bandwidth. So the rise time and the bandwidth So delta F is equal to 1 over 3 T. T stands for T, time of the rise time. And there is an example in the textbook. That's why I put it here to remind myself that I have to work through that example, right? So you have to know how to work through it. The delta F, the bandwidth, is equal to 1 over 3 times the rise time. Rise time is the time taken for the output to increase from 10% to 90% of its final value. And delta F decrease means a rise time would increase. If you decrease the rise time, so the rise time, if you decrease it, I want to be clear why we made this statement. T, the rise time, if you decrease it. And I've given also on the video, if you, for example, if you decrease it, you know, we are just looking at the number. Let's say 1 over 0.1. All right? You decrease it 1 over. So this is 3 times. I'm going to ignore the 3 there. And you decrease this rise time to 0.001, 1,000 times, right? So what is the answer to this one here? 1 over 0.3 is what? It's simply 3 times 3.33 times 10 to the minus 1, right? This is 3 times 10 to the, is it? No, I'm making an error here. Can you all see? What is 1 over? What is 1 over 0.1? Is simply 1 over 1 over 10, right? So this is 1 here, correct? And this is times 3. So look at these numbers. We decreased the rise time, 0.1. What happens to, if you decrease it, if you decrease the rise time, delta F decrease means an increase, it means the rise. The decrease means rise time would increase. So that is just trying to play with the math there. Does that make sense? What I'm trying to convey to you? So a rise time, if you decrease, this is delta F, the bandwidth. If you decrease the rise time, you decrease it, the bandwidth would increase and vice versa. Does that make sense? What I'm trying to illustrate here. And so if there is a bandwidth decrease, it means the rise time increase. That means a slow response, low thermal noise. And we have already said that you can do this with the temperature. The temperature and thermal noise will be related in this case. Oops, what's this here? Okay. Let's go to the next page. Okay, here is an example. Look at this example here. And I've worked on this example. Let's work on it here. What is the effect on thermal noise of decreasing the response time of an instrument from 1 second to 1 microsecond? What is the effect on thermal noise? What's the formula for thermal noise again? Thermal noise equals square root of 4K T R, right? Delta F, the bandwidth. So here, the assumption, what is the assumption that we are making is that you have the same instrument, you have the same resistance, you're going to say operate at the same temperature, right? So that's the assumption we are going to make. Does that make sense? To give us an idea on what happens to the thermal noise. So here is how you can work through this problem. You can say this is at 1, and then This is one way. Okay, two. So the first one, you have the thermal noise at 1 second. Are we together there? Thermal noise at 1 second is going to be equal to 4kT R times 1 second. Are we together there? All this is the square root. Does that make sense there? I'm going to use that. Or those of you can see it as the other thing you can do. Oops, what's happening there? Okay. I went too far. Okay, so that, and at another instance, it is 4 kT R. Okay, it is 1 microsecond. What's a microsecond? So that is 10 to the minus 6 of what? Of a second. Again, remember, these are two. So what we are saying here is, notice, again, this is to the square root. I'm not putting the square root, I'm putting half. That's the same. So what is happening to the noise level, therefore? So notice what you will do. At one point, that is the voltage, and then you divide the two. Are we together? Are we together there? So if you divide the two, then notice this number. Let me put it here. So over, does that make sense? What I'm doing there? So which simply means that notice what happens. This is constant. Sorry there. This is constant. That is constant. Does that make sense? So which simply means it is 1 second over 10 to the minus 6. All this to the square root, which is going to be the square root of 10 to the 6th, which is 1,000. I hope everybody has seen what I've done. Is everybody clear on what I've done there? This is systematically going through it. You're just saying that what happens to the voltage or the Johnson noise, it goes by decreasing it from 1 second. Remember, the bandwidth, you decrease the bandwidth from 1 second to 1/millionth of a second. That means that bandwidth, remember we say Johnson noise is dependent on the bandwidth, not on the frequency. By decreasing it by that 1,000,000 times, remember you decreased it by 1,000,000 times, right? That means the noise level goes up how many times? 1,000-fold. Okay, that's one way of handling it. And I will stop here, pick this up. No, we still have 1 minute. Oh, my phone says it's 8:50 now. Okay, all right. I'll pick it up from here next time, and then make sure you go through the other one. I would have liked to go through this very quickly, but I just told myself, no, it will not be justice to you all. Okay, so have a good day. Okay. Yes,
I sent you an email. I don't know if you saw it.
very late.
Massive. I
When?
was stuck in traffic.
When did you send it?
I sent it at 7:58. I was there since.
Too late. That's fine, my.
Okay, I'm
That's a bad.
sorry.
That's okay. I understand. Thank you.
Oh, yeah, they do.